So the atoms of a given radioactive isotope decay at a very, very consistent and predictable rate. Those rates are so predictable and consistent that they can be used to measure time itself. And in fact, we use some of them to measure time. If a particular object contains a certain radioactive isotope, we can actually use that isotope to determine an approximate age for the object. Now the way we do that, and you'll see the steps here, first we use a mass spectrometer, and that's a device that vaporizes a small piece of the object, ionizes the vapor particles, and then sends them through a magnetic field. And that magnetic field separates the sample into different isotopes based on their mass. And what we'll look for is a ratio of parent to daughter isotopes. And what that means is, parent atoms are the radioactive atom that has yet to decay. The daughter atoms, those are atoms that have already given off their radiation. And the ratio will indicate how many half-lives have passed. So for instance, if we get a ratio of 1 to 7, one radioactive parent atom for every 7 daughter atoms, that would be a 1 to 7 ratio. That indicates that 3 half-lives have passed. And we can measure for more than 1 half-life and less than 1 half-life. Now, the next thing we do is that, we use that ratio to determine how many half-lives or what fraction of a half-life has passed since the object formed. Finally, we would multiply this number of half-lives by the length of 1 half-life for the isotope, and that number is the approximate age of the object in question. Now here, you'll see examples of some parent and daughter isotope combinations. Uranium-238 and uranium-235, which both decay into daughter atoms of lead, lead-206, lead-207. They have very long half-lives. U-238, 4.5 billion years. 10 to the 9th is 1 billion. U-235, 700 million year half-life. That means it would take that long for half the uranium atoms in that object to decay into the daughter isotope. Potassium-40 decays into argon-40, and the half-life there is 1.4 billion years. Carbon-14 decays into nitrogen-14, much shorter half-life, only 5,700 years. If you've heard of carbon dating can determine the approximate age of objects that were once living. Life forms on Earth are made primarily of carbon, so anything that's organic made of carbon, we can use C14 to determine the half-life. So let's look at an example. How would we actually go about doing this? Well, let's take a look here. So imagine we have an old seashell, and the ratio of C14 to N14 is found to be 1 to 3. How old is the shell? Well, first off, this ratio was determined using a mass spectrometer. So we have a 1 to 3 ratio, 1 part C14 to 3 parts N14. Now, if we look at our table then, how many half-lives have elapsed? 1 to 3 ratio. That tells us that 2 half-lives have elapsed. And then, of course, we're looking at C14, N14, right there. So our half-life is 5,700 years. So to do the problem, we're going to take 2 half-lives and multiply that by 5,700. And the number we get there, 11,400 years. So what that tells us is, in any living object, the C14 begins to decay and to not be replenished when an object dies. And think about it, right? When something dies, it's no longer living, it's no longer eating and ingesting food, or it's no longer taking in carbon dioxide if it's a plant. So at the moment of death, it's not replenishing any more C14. So what this tells us is that this seashell died approximately 11,400 years ago. For any object where we can use radiometric dating to determine its age, this is how we would do it. Okay?